All right, today's lesson 8, is comparing relationships with equations. So yesterday we looked at tables and we looked at whether or not we could tell if tables were proportional or not. Now we're going to be looking at equations and deciding whether a relationship represented by an equation is proportional or not. All right, we have something here to notice and wonder, some patterns with rectangles. All right, every time I turn this off, the dogs start barking again, but we'll try this again. All right, so do you see any sort of pattern in what happens as the rectangles are increasing in size? So if we look at each rectangle, we might figure out the area of each rectangle. So just by counting squares, we can see that the first rectangle is made up of 3 squares. So the area of the first rectangle is 3, we'll just say units squared, 3 square units. The second rectangle, we have 1, 2, 3, 4, 5, 6 along one side, and 2 going up this side. 2 times 6 is 12, so the area of that rectangle is 12 square units. This rectangle, we have 1, 2, 3, 4, 5, 6, 7, 8, 9 across the top and 3 across the bottom, so the area is 27 square units. Now, you may have noticed that in going from the first rectangle to the second rectangle, all of the side lengths are twice as large. So on the first rectangle, the height was 1. On the second rectangle, it was 2. The width was 3. On the second rectangle, it was 6. So all of the side lengths got twice as large. If we go from the first to the third, the height is 3. The width is 9. So the third rectangle is 3 times as large as the first rectangle. So if we look at the relationship between area, you might remember from our previous work that area is not going to have the same scale factor as lengths. So if the scale factor to get from the first rectangle to the second rectangle is 2, if we look at the area is not 2 times larger, the area is 4 times larger. So we would multiply times 4. To get from the first rectangle to the third rectangle, we could say we have a scale factor of 3. But to get from the first rectangle's area to the third rectangle's area, that is 9 times bigger. And we had talked before in our scale drawing unit that the area is always going to be the scale factor squared. So if the scale factor is 2, 2 times 2 is 4, and the area is 4 times bigger. Over here, the scale factor was 3. 3 times 3 is 9. So the area is 9 times bigger. So that's the pattern that you should be seeing. So what predictions can you make about future rectangles in the set if your pattern continues? Well, if we were to add another rectangle, I would predict that its sides would be 4 times larger than the original rectangle. And if its sides are 4 times longer, so let's write up here, fourth rectangle, the scale factor would be 4, but the area would be 4 times 4, which is 16 times larger. If we were to look at a fifth rectangle, we would expect that that one would have a scale factor of 5, that all of the side lengths would be 5 times larger, and the area would be 5 times 5, which is 25 times larger. And we could go on and on. Every time for the sixth rectangle, the scale factor would be 6, the area would be 6 times 6, which is 36. And we could go on and predict an infinite number of rectangles that way. All right, 8.2, more conversions. So the other day you worked with converting meters, centimeters, and millimeters. Today we're going to do some more unit conversion. So we're going to use this equation, F equals 9/5 C plus 32, where F represents degrees Fahrenheit, which are is the unit in which we are used to expressing degrees, and C represents degrees Celsius to complete the table. So what this equation is telling us is that if we know what either f or c is, we can substitute it into the equation and solve for f. So if we look at the table, our first row says the temperature is 20 degrees Celsius. So if I go up to my equation, I can say that in Fahrenheit, that would be 9/5 times C, so I'm going to do times 20, and then add 32. If I do 9/5 times 20, I could make that 20 over 1. I can simplify this way. 5 goes into 24 times. 9 times 4 is 36, so we have 36 over 1 plus 32, which is 68. So when it's 20 degrees Celsius, it would be 68 degrees Fahrenheit. If it were 4 degrees Celsius, I can do the same thing. So 9/5 times 4 this time, plus 32. 9/5 times 4 is 36/5. And 36/5 as a mixed number, let's see, 5 goes into 36 7 times with 1 left over, so we have 7 1/5 plus 32. That equals 39 1/5. So 39 1/5, or it might be more common to express temperature using a decimal, so the equivalent decimal is 0.2, 2/10, which reduces to 1/5. Okay, if I'm going to do 175, I'm going to go over here, so I have 9/5 times 175, put that over 1, plus 32. I can reduce this diagonally. 5 goes into 175. Let's see, 5 times 3 is 15. I would have 2 left over, and 5 times 5 is 25. 35 times 9, let's see, I'll just do that up here. 9 times 5 is 45. 9 times 3 is 27, plus 4 is 31. So we get 315 plus 32, which is 347. Wow, that would be really hot. We would all burn up if it was actually that hot outside. All right, the question then asks, is this a proportional relationship? Why or why not? So in order to tell if it's a proportional relationship, recall that we need to figure out, is there something we can multiply the numbers in the first column by to get the numbers in the second column? And we can figure out what that is by dividing. So if I were to divide 68 by 20, and I'm going to use my calculator for this one. 68 divided by 20, actually I didn't need to use it for that, gives us 3.4. If I do 39.2 divided by 4, I get something different. I get 9.8. And if I do 347 divided by 175, I get some sort of long decimal that starts with 1.98 and keeps going. So the point here is the ratios are not the same. So I'm going to write my answer. I think it'll fit down here. No, it's not a proportional relationship. The ratios are not equivalent. That is the way to check to see if a table is proportional, is by checking to see if the ratios are equivalent. If they are not, then it is not a proportional relationship. Okay, now we're going to use a different equation. This equation is C equals 2.54n, where C represents the length in centimeters and n represents the length in inches to complete the table. So n represents the length in inches, so this side is n and this side is c, or the length in centimeters. So to find c, we're going to do 2.54 times n. So if n is 10, we're going to do 2.54 times 10. When we multiply by 10, we can just move our decimal one place to the right. So this becomes 25.4 centimeters. If the length n is 8 inches. Now I can do 2.54 times 8, and 2.54 times 8 is 20.32, or 20 and 32 hundredths. Okay, for 3.5, I'm going to do 2.54. Since this is a decimal, I'm going to express 3.5 as a decimal. It would be 3.5. So 2.54 times 3.5 is 8.89, or 8 and 89 hundredths. Okay, is this a proportional relationship equation? So this equation that we had up here, was that a proportional relationship equation? Well, let's see if the table tells us that it was proportional. If we do 25.4 divided by 10, we get 2.54. If we take 20.32 and we divide by 8, we also get 2.54. And if we do 8 and 89 hundredths divided by 3.5, we get 2.54. So we would say that yes, that equation must be a proportional relationship equation, because all the ratios in the table it produced are equivalent. In the table it produced are equivalent. Now we're going to do 8.3, total edge length, surface area, and volume. Here are some cubes with different side lengths. So remember, a cube is a three-dimensional shape whose sides are all the same length. All of the edges are the same length. So this is 3, this is 3, across here is 3, they're all 3. For this one, they're all 5. For this one, they're all 9.5. We're going to complete each one of these tables, and then we are going to talk about some of these questions. So number 1 says, how long is the total edge length of each cube? That's what's going to go over here. So if we look at the total edge length, one of the sides is 3 units long. And we need to think, well, how many of those sides are there? How many of those edges are there? So just from what we can see in the front, there's one. Actually, let me use a color that you can see here. How about some orange? So we have 1, 2, 3, 4, and then we're going to have 5, 6, 7, and there's going to be another one going through here, 8. Along the back, we're going to have 9, 10, this one you can't see, 11, 12. So we're going to have a total of 12 edges. So the total edge length of this cube would be 12 times 3. There are 12 edges. Each one of them is 3 units long, so the total edge length would be 36 inches. Okay, we would find the total edge length of the next cube the same way. There's still going to be 12 edges, and each edge is 5 units long, so 12 times 5 is 60. For this cube, its sides are all 9.5 units long, so if we take 12 times 9.5, we get 114. Now if we had any side lengths, we had a side length of S, we would have 12 sides or 12 edges altogether. So we would just say that the total edge length would be 12S. Number 2 says, what is the surface area of each cube? Well, you probably need a refresher as to what surface area is, and we'll be working on that a lot later in the year. But surface area is the area of all of the faces added together. So a face, let's use a little pink here, a face would be, this would be one face. So this cube would have 1, 2, 3, plus there are 3 faces that you can't see. There's the back face, the bottom face, and the left face. So each cube has a total of 6 faces. The area of one face, if the face is 3 by 3, then the area of each face is 9 square units. So the area of one face is 9 square units. We have 6 faces, so 6 times 9 gives us an area of 54 square units. So I'm not going to put square units over here every time. I'm just going to say 54. If the side length is 5, I need to find the area of this front face and then multiply it by 6 because there are 6 faces. So this face is 5 by 5. 5 times 5 is 25, and 25 times 6 is 150. For the large cube, each side is 9.5 units long. I'm going to find the area of the front face and then multiply times 6 since there are 6 faces. So 9.5 times 9.5 gives me the area of the front face, which is 90.25 square units. I'll multiply that times 6 and I get 541.5. Now, if I have a side length of S, let's think about what we need to do to any side length in order to find the surface area. So the first thing we did for all of these is we multiplied the side length times itself. So we did 3 times 3, 5 times 5, 9.5 times 9.5. So we would need to do S times S. And we can write that as S with a little number 2, S squared. So we did each side, we found the area, and then since there were 6 faces, then we multiplied times 6. So we have S squared times 6, which we can just write as 6S squared. All right, the last thing, number 3, asks us to find the volume of each cube. So when we're finding the volume, we're finding out how many little unit cubes would fit inside. So I'm going to just draw on the large one here. It would probably be the easiest to see. We're finding how many of these little cubes would fit inside the big cube. And we find volume by doing the length times the width times the height. So for the first cube, we would do 3 times 3 times 3, which is 27. For the next cube, we would do 5 times 5 times 5, which is 125. For the large cube, we would do 9.5 times 9.5 times 9.5, and we get 857. Whoops, I wrote that wrong. 800. Come on, erase. There we go. 857.375, or 375 thousandths. So what did we do? We multiplied S times S times S. And another way we can write that is S with a little number 3. That means we're going to multiply S 3 times. We call that S cubed. All right, number 4 asks which relationship is proportional and how do you know? So to find out whether it's proportional, we need to see if there is something we can multiply the numbers on the left by to get the numbers on the right. So we're going to find that by dividing. Let's take a look at the edge length table first. 36 divided by 3 is 12. 60 divided by 5 is 12. 114 divided by 9.5 is 12. If we look at the surface area table, 54 divided by 3 is 18. 150 divided by 5 is 30. 541.5 divided by 9.5 is 57. So this table is not proportional. It does not have a constant of proportionality. If we take a look at the last table, 27 divided by 3 is 9. 125 divided by 5 is 25. And 857 and 375 thousandths divided by 9.5 is 90 and a quarter, 90 and 25/100. So this one is also not a proportional relationship. So which relationship is proportional? The edge length to the side length is proportional because it forms equivalent ratios, or because the ratios are equivalent. Now it wants us to write equations for each table. This is actually going to be pretty easy to do because we've already filled in this last row in the table. So for this one, I'm going to use L for edge length. The edge length would equal 12 times the side length. For surface area, I'm going to use SA for surface area. The surface area is 6 times the side squared. And the volume, we'll use V, is S cubed. All right, looks like we have an extra page in here that we don't need, so let's just move on. 8.4, all kinds of equations. We have 6 different equations, and I would like you to pause the video for a second and predict which of these equations represent a proportional relationship. And then we're going to come back and do a little work, and we're going to think about which ones represent a proportional relationship. All right, so we are going to take each of these equations and we are going to fill out a table based on the equation. So the first equation, y equals 4 plus x. Whatever x is, we're going to add 4 to it, and that will be y. So when x is 2, 4 plus 2 is 6. When x is 3, 4 plus 3 is 7. When x is 4, 4 plus 4 is 8. And when x is 5, 4 plus 5 equals 9. Okay, now we're going to check these ratios to see if they are equivalent. 6 divided by 2 is 3. 7 divided by 3 is not 3. So we can actually stop right there and we can say it is not 3. We don't even have to find out what it is because the ratios are not equivalent. So this equation did not work out to be a proportional relationship equation. All right, let's move on to the next one. Y equals 4x. So when x is 2, we can do 4 times 2, y would be 8. When x is 3, 4 times 3 is 12. When x is 4, 4 times 4 is 16. And when x is 5, 4 times 5 is 20. Now let's take a look at the ratio. Y over x, 8 divided by 2 is 4. 12 divided by 3 is 4. 16 divided by 4 is 4. And 20 divided by 5 is 4. So this equation does represent a proportional relationship. Okay, let's take a look at this one. Y equals 4 over x. Okay, so if x is 2, 4 over 2 means 4 divided by 2. 4 divided by 2 is 2. If x is 3, 4 divided by 3 is 1 and 1/3. If x is 4, 4 divided by 4 is 1. If x is 5, 4 divided by 5 is just 4 over 5, or 4/5. Okay, let's find the ratio of y to x. So 2 divided by 2 is 1. 1 and 1/3 divided by 3 is definitely not 1. We would have to have either both of them would have to be 1 and 1/3, or both of them would have to be 3 in order to get 1. So I don't even need to find out what it is. I can see that the ratios are not going to be equivalent, and this equation does not represent a proportional relationship. Okay, moving on to the next one. Y equals x over 4. This means x divided by 4. If x is 2, 2 divided by 4 is just the fraction 2/4, which reduces to 1/2. If x is 3, 3 over 4 is just 3/4. If x is 4, 4 over 4 is like 4 divided by 4, that's 1. And if x is 5, 5 over 4, 5 divided by 4 is 1 and 1/4. Now let's see what we get if we do y divided by x. 1/2 divided by 2 is going to give us 1/4. You could put this in the calculator as 0.5 and divide it by 2, or you could think of 1/2 divided by 2 over 1. We would keep it, switch it, flip it, and 1/2 times 1/2 is 1/4. 3/4 divided by 3, if we keep it, switch it, flip it, that's like 3/4 times 1/3. The 3's would cancel out, and we get 1/4. 1 divided by 4 is 1/4, and 1 and 1/4 can be expressed as 5/4. 5/4 divided by 5 is like 5/4 times 1 over 5. The 5's cancel, and we have 1/4. So all of our ratios are the same. So y equals x over 4 also represents a proportional relationship. Okay, looking at y equals 4, and this tiny little x up there is an exponent. So it's saying 4 to that power. So if x is 2, it's like saying y is 4 to the second power. That means we multiply 4 times 4, and that would be 16. 4 to the third power means that we multiply 4 3 times. So we would do 4 times 4 times 4. So 4 times 4 is 16, and 16 times 4 is 64. 4 to the fourth power means that we do 4 times 4 times 4 times 4, and when we do that, we get 256. 4 to the fifth power means we multiply 4 5 times. So we do 4 times 4 times 4 times 4 times 4, which works out to be 1024. So now if we find the ratio y over x, 16 divided by 2 is 8. 64 divided by 3 is 21 and 1/3. So we can already see the ratios are not the same, so this equation does not represent a proportional relationship. Last one, this one has another exponent. The exponent is always 4, and x is going to be different every time. So if x is 2, we have y equals 2 to the fourth power. That means 2 times 2 times 2 times 2. 2 times 2 is 4, times another 2 is 8, times 2 is 16. If x is 3, we have 3 to the fourth power. So we're going to multiply 3 times 3 times 3 times 3, and we get 81. 4 to the fourth power is 4 times 4 times 4 times 4, which gives us 256. And finally, 5 to the fourth power is 5 times 5 times 5 times 5, which is 625. So again, if we do 16 divided by 2, we get 8. 81 divided by 3, we get 27. So these numbers are not the same. This is also not a proportional relationship equation. So we only had 2 out of the whole group that were proportional relationship equations. What do the equations of proportional relationships have in common? So if we look at both of these, the first one is the form that we actually learned about earlier. We said that proportional relationship equations have to be in this form. Y equals something times x, and that something is the constant of proportionality. This one looks a little different. This one has division instead of multiplication. This one is saying that y equals x divided by 4. Well, remember when we divide by 4, that's the same as multiplying by 1/2. So another way to write this equation is y equals 1/4 times x. So when we look at it that way, it fits in the same form as the other equation. We have y equals the constant of proportionality times x. All right, so lesson summary. How can you tell whether an equation represents a proportional relationship? I would encourage you to pause the video and think about how you can tell whether an equation represents a proportional relationship. Write your answer and then come back and check. All right, so the first thing that we can do to tell whether an equation represents a proportional relationship is to see if it's in this form. If it's in the form y equals kx, where we multiply the constant of proportionality times the first quantity to get the second quantity, that equation would represent a proportional relationship. If we add anything to it, so say we have y equals kx plus 2, that's not going to be proportional. If we have something like y equals kx squared, that's not going to be proportional. It just has to be a plain x. If we have something like y equals kx to the fourth power, it would not be proportional. If we have something like y equals 4 over x, that one's not proportional either. But if we were to write it out this way, if we were to say y equals x over 5, this one is proportional because it could be written as y equals 1/5 times x, which fits this form. So that's the first way you can tell. Another way that you can tell, if you're really not sure, is to use the values that you have for x and y, or you could create some values and make a table and then check to see if the table makes a proportional relationship. So for example, if you had y equals 6x and you wanted to know if this was a proportional relationship, you could make a table of x and y, and you could actually just make up some numbers to be x. You can pick anything you want to be x and figure out what y would be. I'm just going to use, say, 1, 3, and let's use 6. So if x is 1, 6 times 1 is 6. If x is 3, 6 times 3 is 18. And if x is 6, 6 times 6 is 36. So if I divide all of these ratios, 6 divided by 1 is 6. So let's make a third column here, y over x. 18 divided by 3 is 6. 36 divided by 6 is 6. So this one worked, and I can tell also from the table that that is a proportional relationship.